Okay, so I want to move on from measures of central tendency and start to talk about something a little bit different. So we're going to start with these two examples, two different distributions of scores. Let's call this one B. Let's call this one distribution C, just because we've used A and B before, and we'll just do B and C. And let's remember what these frequency histograms represent, right? These are X values down here, right? These are X values. This is along some number line. And then there's an implied frequency axis, the y-axis. And I'm going to create a problem for us, okay? I want the problem to be sort of explicit so that, to make a point, and then when we get into subtler differences between distributions, we'll be able to deal with those as well, okay? And so we also need to remember, right, that these curves simply represent where the tops of the stacks of boxes are, right? So there's all sorts of boxes in here, okay? Likewise, I mean the same thing here, okay? Here we go. And so we just need to remember that, again, that this is not super challenging, but it's really worth remembering what that curve represents, because most of the time people are not going to fill in the curve with these boxes that you see. Okay, so let's assume that both of these are symmetrical about the the vertical axis here, so like this. Okay, let's assume that they're symmetrical. And so that would mean that 50%, if it's symmetrical, 50% of the boxes are here and 50% are here. So this would be our median, okay? The median is the 50th percentile, the place where 50% of the scores fall at or below, okay? Also, we can see that this is the mode, because the mode is the most frequent score, okay? And in fact, this will end up being the mean as well, the balance point. And let me just put a number in here, just for the sake of our discussions. Let's say the mean and the median and the mode are all at 72. Okay? And let's say the highest score is 97. And the lowest score here is, let's say, 45. Okay? I mean, I guess if we want it to be, well, I guess that works out. If we want it to be symmetrical, maybe we should do, so this is 15 above, this is 15 below. Let's make this a 47. Okay? That way it's really nice and symmetrical. Okay. Let's, for the sake of argument here, say that there are 100 people in this distribution. That would mean that there's 100 blocks, right? Let's go over here and do the same thing. Let's say that there's 100 blocks here. Of course, now we can understand that the blocks are distributed differently. Once again, this would be the median. If this is symmetrical, this would be the median, right? It's the highest point, so it would be the mode. And it's the balance for this distribution. And so it would be the mean as well. And let's, for the sake of argument, say that we also found that the mean for this distribution was 72. And let's say that the highest score here is a 97 and the lowest score in this distribution is a 47. So what would be the range, by the way? What would be the range here? Well, the range would be what? The range would be 51, 97 minus 47 plus 1, okay? Likewise, the range here would be 51. If we go from 97 to 47, we add 1. Range is 51. Okay? So we have two different distributions here. But the problem is that the descriptive statistics that we have developed thus far do not differentiate between these two curves. Okay? So that if I reported the sample size or the population size, whatever you want to consider it, same, same. Range, same, same. Mean, median, mode, same, same. And I've created that because I want you to appreciate, understand, I want you to see that we can have two different distributions that are quite different. They look really quite different, and yet all of our descriptive statistics thus far cannot differentiate between these two. And so what we're going to do here is try to develop a new descriptive statistic that will allow us to differentiate between these two curves. Because statistics were not discovered, right? Statistics weren't laying around under a rock. They're really invented. And in this case, I want us to invent something that would differentiate between these two curves. Okay? So I'm going to get rid of some of this stuff here. Clean things up a little bit. Okay? Let's clean this up a little bit too. Okay? And the first question I want to ask, and you know by now from watching the videos that I'm going to ask you to think about these things. It's not really learning anything if you don't sort of use your brain and get involved. Think about, so here is the problem, right? How can we solve this problem? Because most of the time, if you're going to be a professional when you get out of college and get a good job, you're going to be faced with problems that need to be solved, not with, a fact that needs to be known, because we can just Google it nowadays or ask Alexa or whatever. Most of the things you're going to deal with are problems that you've not seen a solution to previously, right? So the first thing we have to ask ourselves is, well, how do these two graphs differ? I mean, what is the difference between them? How would you describe the difference between them? Once we identify that, then we might be able to solve the problem, and that is come up with a number that represents the difference between these two. And so I would ask you, and this is, we're doing this online is a little bit of a disadvantage, because I would like to have us talk about this a little bit more. What is the difference? What is the difference between these two graphs? If you were trying to describe this to a friend, these two graphs, and just describe the difference, and I'm not asking you to try to guess at some statistical concept. I'm asking you as an adult with, just looking at these two graphs, what is the difference? Well, I think that the descriptions might go something like, this is taller and skinnier, and this is maybe flatter and fatter, okay, or something like that, which is a good start. which is a good start. And then I would push you and I would say, okay, well, what is causing this one to be skinnier and taller? And what's causing this one to be fatter and flatter? Okay? And here's what it is. I mean, if we look here, there's a lot more people that are at the mean. Let's talk about the mean, since these are fairly normal curves. The mean is our gold standard for central tendency. So let's talk about that. And when we look at these blocks, what we're seeing here is there's a lot more of the blocks at the mean than there are here. Okay? Now, in both situations, the mean and the mode are at the same spot. But in a way, this one is, I mean, for lack of a better term, this one is modier, right? There's more people out of the 100, there's a lot more people here than here. There's still quite a few people here, but not as much. Likewise, the complementary description here, and that's complementary with an E, right, is that as we move away from the mean, there are fewer blocks in distribution C than what we would see in distribution B. Now, we don't capture that from the absolute range, right, because both distributions have the same range. Both go from 97 to 47, 97 to 47. So we can't capture the difference here just looking at the range, but we can start looking at the distribution of the blocks within the range, and we see that there's a lot of boxes close to the mean here, not as many far away, not as many close to the mean, more far away. Okay? That's the first step in trying to solve this problem. Okay? I want to start from the ground floor up and have you guys thinking about this stuff rather than coming in and saying, putting stuff on a board and saying, this is how you do this. Okay? I don't find that to represent true education as much as sort of looking at the problem, seeing if we can analyze this. Okay? So really what we're saying here is within the same range, here and here, we have blocks here are more what? Spread out. Okay? Over here, the blocks, I mean, in an absolute sense, 97 to 47, it's the same. But within that range, the boxes are much more concentrated in the center. Okay? So really what we're talking about here, the dimension that differentiates these two graphs is spread outness, okay? Or scrunched upness, if you want to say that. These blocks are more spread out within the range. These blocks are not as spread out within that overall range. Okay? Would you agree? I hope that you would agree. And we don't need to make it any more technical than that right now because we're trying to solve a complex problem here. So let's keep it simple for the moment. And really what we're talking about here is spread outness. Okay? And if you're comfortable with this term, I think that you're on the right track for sure. And this will set you up. It will really set you up for the rest of the semester. I mean, this concept is what we're going to be focused on for a lot of the rest of the semester. This notion of spread outness. Of course, when you say something is spread out, or when you say something is scrunched up, I would ask you, like, spread out from where, right? Scrunched up around where? Well, really, we're talking about, the mean as the reference point. So relative to the mean, these numbers are more spread out. Relative to the mean, these numbers are less spread out or more scrunched up. I'm okay with those terms for now, okay? we're going to replace it with something called variability. Mathematicians sometimes talk about dispersion, okay? But both of those terms really generally refer to spread outness. And so I like to bring students in without the jargon first, and then we'll get to the jargon, right? That's just something we'll replace with spread outness. So we're really talking about variability here. Variability is sort of synonymous with spread outness. Dispersion is another term. And by the way, dispersion shouldn't be a new term for college students. I mean, if I said, here are some seeds and I want you to disperse them around my lawn, then you would spread them out, right? Spread them out. Dispersion. Spread outness. Variability. Okay? These numbers are more variable. These numbers are less variable. But here's the essence. Spread outness. Spread out from where? Well, spread out from the mean. Okay? That's what I'm talking about. So, can we come up with a value, a number that represents spread outness, okay, that represents variability or dispersion? And the answer is, well, I think so. Let's see. When I say spread outness, I'm saying something like this number is more spread out or further away than this number from the mean, right? There are not as many numbers that are spread out in this. There are more numbers that are spread out over here. Okay? And so I'm going to ask you this. I'm going to say, all right, well, suppose that we took this number here, okay, and let's put an x value on it. So let's say that this number is x equals 82. And what did we say? We said the mean was 72. Okay. Now I'm going to ask you a question. How far away is this score from the mean? Well, I hope that wasn't challenging, right? How far away is this score from the mean? And the answer is, it's 10 points from the mean, right? And I'm going to say, what was the mathematical function you used to determine that? And again, I hope this is not too challenging for you. I know it's not. And that is, you took the score, you subtracted the mean, and you got your answer, right? So you took 82, you subtracted 72. The answer that you gave me was 10, okay? So this is the formula that we're going to use to determine how far is a score away from the mean. All right? Hey, listen, it's going to get more complicated. It's going to get more complicated. So if you're good here, I'm going to take you step by step through this process, okay? This is called the deviation score. That is, how much does this score deviate from the mean? Well, you take the score, you subtract the mean, it deviates by 10. Okay? If we went over here and I took this score, which is x equals 72, right? What's the deviation score for this score? Well, I'm going to take x minus my mean and get the answer. So 72 minus 72 equals 0. And of course, that should make sense. This score does not deviate from the mean. This score deviates by 10 points. Everybody with me? So x, let me do this. Make some more room here. This is distribution B. This is distribution C. So this thing that we call a deviation score tells you how far away from the mean you are. Okay? You did it here. You did it here. I mean, let's just understand that this tells us how far away from the mean you are. I mean, this is not your score on the exam, right? Your score is here. This tells you how far from the mean. Everybody good? All right, now we're going to make another leap here in a way, because I've heard this before in relationships. I'm sure that you've heard it before too. It's kind of funny. Sometimes your partner says, you know, it's not always about you, right? What? And I'm always like, yeah, it's not always about you either. Anyway, but what I want to do is I want to describe this entire distribution. I want to describe this entire distribution. I don't want to just look at this person and say, you're 10 away from the mean. I don't want to look at this person and say, you're 0 away from the mean. I don't want to look at this person and say, you're 15 away from the mean. I don't want to look at this person and say, you're 2 away from the mean. What I want to do is I want to compare these distributions in toto, that is, as a whole, okay? But this is a very, very important building block, because what we're going to do here, is we are going to get the deviation scores for all 100 people. For all 100 blocks here, we're going to get the deviation scores. So these scores that are right in the mean will be 0, and this might be 5, and this might be 10, and this might be, you know, okay? So we're going to take into consideration all, how many blocks are there? All 100 blocks. We're going to get all of the deviations and look at them as a group. Well, you know what? We already have a symbol that will allow us to do this. This is why this course sometimes challenging, but I find it stimulating and refreshing, because what we learned about before, we bring with us. This is a cumulative class. It's not just separate factoids. So we know how to add up a bunch of things. And how do we do it? Here's how we do it. We're going to do this. Okay. Now things are getting a little bit more complex. I told you that they would. But let's start with the simple and work our way up. Okay. What does this tell us? This tells us for any score how far away from the mean we are. This tells us do it for all 100 blocks. Do this 100 times. Yeah, do this 100 times. So I'm going to do that for C. I'm going to do it for B. Can anybody anticipate what will happen here? For C, there's a lot of people. A lot of the 100 will get a score of 0 for their deviation score. There will be some that have large deviation scores, right? There will be some that have intermediate deviation scores. But over here, there are fewer that will have a deviation score of 0, and there are more that will be deviant further away. All right, let me say that again, right? For this distribution, there's going to be a lot of blocks that have a deviation score of 0. Over here, there will be some too, but many more zeros than here. For this distribution, there's going to be a lot more that are at +8, +9, +10. Over here, not as many, okay? So when we do this 100 times for B, and we do it 100 times for C, and then add all those together, you're going to get a number, folks. You're going to get a number, okay? You're going to add all these 100 up. You're going to add all these 100 up. You get a number. Which one of these distributions do you think will give us a larger value for the sum of all the deviation scores? Okay, So this is the sum of deviation scores, this formula, because we're adding together all of our deviations. If this is your exam score, you would be 10. If I got the 72 on the exam, mine would be 0. If someone else got a 92 on the exam, theirs would be 20. If somebody else got, and so on and so forth. We're going to add that list of 100 numbers up. A lot more zeros here, fewer zeros here. Okay? Have I given you enough time? What do you think the outcome will be if we compare the sum of the deviation scores here and the sum of the deviation scores here? Which one will be larger? If you said B would be larger, oh, beautiful. You are on the right track and you understand what I'm talking about, okay? If we add up all these deviation scores, B, the sum of deviation scores should be larger for B than for C, okay? If you have a question, please drop me an email. However, there is a little bit of a, and I mean, that is a golden concept. Golden, golden, golden. If you thought this would be larger than this, you got it. And we're successful. But there's a little bit of a glitch. There's a little bit of a glitch here, okay? And that is because when we use this formula, x minus mu, what we're going to see is any of the blocks on this side of the curve will give a positive value. Any blocks on this side of the curve will give a negative value. Likewise here, anything above the mean, if we use this formula, right, we'll get a positive number. Anything below will give you a negative number. And we're going to finally be able to understand even a little bit more about the mean. What the mean does, the position of the mean balances, and remember we talked about the fulcrum. What does it balance? It balances the deviations. And in fact, when we do the sum of deviation scores, it will always, always, always be equal to 0 by definition of the mean. The mean is at the place where the deviations add up to 0, that is, the deviations balance. Okay? But remember, folks, and I'm going to do this quickly here, right? We still have to keep in mind, because it can be misleading here. Remember that the mean doesn't necessarily balance the number of blocks. In each of these distributions, it does, okay? That's a coincidence. And I'm not going to change it, but I'm going to remind you here. So this is, remember the mean was 4 in this distribution, remember from your notes. So it's -2, -2, -2 for deviations, and then +6. So those, when we add those up, it'll be 0. But I just want to make sure, you need to, put an asterisk in your notebook. You need to know that it's not always the case where for every +10 there's a -10, for every +5 there's a -5, for every +1 there's a -1. That's not necessarily the case. When you have a symmetrical distribution, it is. But remember our little distribution here that helps remind us. It's not the number of blocks that are balanced. It is the deviations that are balanced. Okay. So why the hell do we do all of this stuff, right? That's the question. Because if this is 0 and this is 0, then we have a statistic that doesn't differentiate between these two curves. And so it might seem like I've brought you down the wrong path, and that is absolutely not the case. You need to trust me, okay? a little bit, because the concept is so golden and so good that as we start with this building block, it's really a measure of spread outness, right? Of deviation. This is the building block of spread outness. This is the building block of spread outness. I did this because I said, listen, I don't want to just look at the spread outness for one score. I want to see this as a total group so I can compare, okay? So the concept is good. In fact, it's golden. But this is a kind of a weird nuisance that it will always add up to 0. No matter what the shape of the distribution, the sum of the deviations will be 0 by definition of what the mean means, okay? So we're going to fix this mathematically, and it's an easy fix, okay? Here's what we're going to do. Instead of doing the sum of the deviation scores, we're going to do this. We're going to square it. So it's the sum of squared deviation scores. The sum of the squared deviation scores, okay? And it actually has a name. It's called the sum of squares, SS, same as my initials. I think my mother must have known something, right? This is the sum of the squared deviation scores, sometimes known as the sum of squares. What have we done in this case? Well, if we look at a score that's 82, we know that that's going to have a deviation score of what? X minus mu equals 82 minus 72 equals 10. If we have a score down here that's at 62, what's our deviation score going to be? Well, it's going to be 62 minus 72 equals minus or negative 10. This is a positive 10, okay? Now, conceptually, which one of these is further away from the mean? That's right. The answer is they're equally distant from the mean. They're equally deviant. They're equally deviant, but the numbers are not equal. This is a minus, this is a plus, right? A negative and a positive. But that's just telling us this is higher than the mean, this is lower than the mean. If I square these values, this becomes 100, this becomes 100. It's a little bit of mathematical magic, right? Now we can say these are equally deviant. Even they're not. Trust me on this one, okay? It's not saying it's 100 points from the mean, but I'm saying the squared deviation values are equal, okay? Once we do this, we're getting rid of the negative sign. That's what squaring does. We will take the square root later and fix it, retrofit it, okay? But for right now, what I want to do is I want to do sum of square deviations. When you do the sum of the square deviations, guess what happens? Guess what happens, you guys? If we do the sum of square deviations, we're getting rid of the negative numbers. Now what we see is, if we do the sum of squared deviation scores, we see a larger number for B than we do for C. Okay? In this case, we see a larger number here than here. And in fact, the sum of the deviation scores is a measure of spread outness. If you were sitting in a classroom with me, I would have you repeat this 3 times, the whole class, because this is essential for understanding the rest of the semester. Okay? Sum of squared deviations is a measure of spread outness. We're going to get a single number, okay? I mean, we'll do some examples. The sum of the square deviation scores, also known as SS or sum of squares is the shorthand version, is a measure of spread outness. If this curve is more spread out, and we agreed that it was when we started, and this distribution is less spread out, then when we calculate the sum of squares, we're going to get a larger number here than here. okay? Spread outness is also called variability or dispersion, and we're going to get used to calling it variability. But boy, when you hear the word variability, you should be thinking to yourself, spread outness, spread outness, okay? Sum of squares is a measure of spread outness, and this is the formula. A lot of statistics teachers would come into the class, give you this formula, have you do the math, and get some numbers. And not all statistics professors, right? But I know the ones that I've had, they come in, they're working from top down. And I don't like that, because if I don't understand the concept, what good, what use is the number, okay? Sum of squares is a measure of spread outness. It's a measure of variability, also known as dispersion. This is the conceptual basis of that. And in fact, now I'm going to show you how to do this in terms of computations. But now we're going to be able to say, here's the mean, here's the median, here's the mode, here's the range, and here's the sum of squares. Okay, and the sum of squares tells us spread outness. Now, the range is a measure of spread outness too, but we have to be careful, because one number can make it look like the scores are really spread out. We'll talk about that a little bit later. This is another measure of spread outness, sum of squares. Okay, so let me do this. I'm going to erase all of this. Okay, and let's do an example. I'm just going to use numbers here without putting any, we're just going to practice some computations. I usually say these numbers represent blah, 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 but for now, let's just see how this works. Let's do group D and group E, okay? And let's do this. Group D is composed of these numbers. Let's see. Okay. And here's what I want you to do. I want you to get the mean for group D, and I want you to get the sum of squares for group D. Sum of squares is this formula, okay? Let me explain what you need to do here. First of all, we need to get the mean. That's what you're going to do here. Then you're going to take each score, subtract the mean, square it. So whatever the mean is here, it's going to be 6 minus the mean squared, 9 minus the mean squared, 10 minus the mean squared. Everybody got me? Then we're going to add all those together. So let's get that value. Okay. Group E. Let me do group E. Let's do this. Yeah, let's do this. Okay. I'm just checking here. Okay. So we're going to get the mean for group E, and we're going to get the sum of squared deviations for group E. Again, we're going to, once we get our mean, we'll take each score, subtract the mean, square it, and then add all those together. Okay? So once we get our mean, we're going to say 572 minus the mean squared, 568 minus the mean squared, 569 minus the mean squared, okay, and so on and so forth. So let's do that, and then we will, the next video, we'll pick up from there. Okay, I would advise you to watch this video again. This will set us up for the rest of the semester. If you need to understand the concept, and then we're going to work with the computations. Okay, sum of squared deviations. This tells us how far a score is from the mean. This gets rid of any negative. This tells us do it for all of the scores and add them together. All right. So next video we'll see how you did, and then we'll move on from there.